This is, oh, by the way, the job fair is tomorrow. So if you're interested in a job, you should tune in tomorrow. There's a Zoom link here. I'll have a class, which I think is 129S as usual. But, if you're in this class, you can just watch the video later. I recommend tuning into the job fair. All right. Anyway, so here we are on 127. And we're up to chapter 3. So I'll start by talking about that. And then I'll do some demonstrations, starting with 103, which is not on this list, which is the SQL injection, which was broken, but now I have fixed it, or so I believe. We will see if it works. So let's start with 3 here. All right, so we're going to talk about, let me make sure I'm in the right chapter. Yeah, protection rings, syscalls, assembling, linking, and using objdump and strace to look at how files run, and nulls and spawning of shells. So we'll start with system calls. When you want to do anything that involves connecting to the hardware, you have to connect to the operating system. You have to make a system call into the kernel. So shellcode is code written in assembler and translated into hexadecimal opcode, so it's raw binary machine code. And the point of this is you will inject this into a system. If you have a vulnerability that lets you execute some code on the system, then you try to put shellcode on the system, which gives you remote control of the system. So typically what you do is you spawn a command line shell, so you gain the ability to execute arbitrary command line commands.
Does shellcode leave any trace?
Is it easy to trace? It's a good question.
Any trace?
Is easy.
Does it leave any trace?
Does it leave any trace? Well, if you put it on the hard drive, it might. If you put it in memory, normally you execute it directly. If we were going to do it here, we're going to execute it in memory with buffer overflows and such. And if you do that, I don't think it leaves any trace. The only thing is you might spot it coming in on the network. And it does change the running of a program and often launch a new process. So but those are pretty subtle artifacts.
It wouldn't touch the registry, does it?
No, it would not, normally it would not touch the registry or the hard drive. So it's pretty hard to find. I mean, in principle, if you know what it is, you could look for it. And I think that's how your antivirus works. But yeah, by itself, it's pretty innocuous, pretty hard to spot. It's going to make a network connection out. That's probably the most obvious thing you would notice. It'll make a network connection to the command and control server, and you might notice that as a known malicious server. That's probably the most obvious trace.
Trigger a trace in registry.
What would change the registry is typically when you install software or change settings. So,
when you run it would not.
Well, shellcode launches itself in memory. Now, the persistence mechanism to make it restart, that usually involves a registry change. So if you execute shellcode like Metasploit shell on a box to gain control right now and issue a few commands, that would be hard to detect. But if you want it to be persistent, you have to make it restart on reboot. And that typically involves writing something you can detect. You're going to need to put something in the registry or put a file in the startup folder or something like that, and that's going to be a trace to look for. So if you think of the attack matrix, code execution might be hard to detect, but persistence and lateral movement are easier to detect, and command and control are easier to detect. So you just have to decide what your attack consists of. These are very good questions. So syscalls are how you execute kernel routines, and so I can get input from the keyboard, put output on the screen, execute a file, exit a process, and so on. So syscalls are how someone in user mode, where all your programs run, can execute code in protected kernel mode, which is where the connection to the hardware is. So this is the protection rings. All modern processors have 4 protection rings, of which only 2 are used. Ring 0 is kernel mode, and that is the processes running in this mode have complete access to all the assembly language instructions in the processor, including the ones that touch hardware. Ring 3 is the least privileged, that's user land. This is where everything you launch from the desktop or the command line runs. And so if you want to do anything privileged, like anything involving touching the hardware, you have to make an API call requesting something in the kernel to do it for you. And the way that's done is with this process called a syscall. You call the system asking it to do something that you don't have the privilege to do. So protected kernel mode prevents user applications from compromising the kernel. This way, if your user land application crashes, it will stop, but the kernel will not stop. So the machine will continue to run, and now it can pop up an error message, and you can restart that process or something. That's the idea, is to protect your operating system is why it's designed this way. So if you attempt to execute access kernel memory or execute a kernel restricted command from user mode, you'll just get an exception. It won't do it, you'll raise an exception. So syscalls are how you do a privileged process from userland, and libc is the standard C library that does things like print and input and everything else, and they're just wrappers around syscalls. Syscalls are the heart of everything. So libc you'd call a libc function, and this way, if the syscall is changed, they'll just update libc to keep up with it. So libc is just a convenience to perform a syscall, really. So there are various ways to implement a syscall. The most common old-fashioned way was int80. This is an interrupt 80, a special signal created in the processor that says stop whatever you're doing and execute a syscall. And it will then look in EAX to find the syscall number, which tells it which syscall activity you're trying to perform, and then it'll have other arguments in other registers, and that's it. You execute int80, so you put the arguments in registers, execute int80, and then the CPU will execute this system call. So the number is an integer in EAX, and then you can have up to 6 arguments in these other registers. If you need more than 6 arguments, then you put a pointer here to a data structure in RAM that contains all those other arguments. So let's try this. I've got Debian, I'm doing it on Intel, so what I've got is a remote shell into my private cloud Intel machine. So this is Debian, I think this might be Debian 10, but it's Debian 10 or 11 running on Intel. So these demonstrations should work. Let me just make them fit on my screen. All right. There, all right, that should be reasonable. Okay. All right, so let's look at exit. Let me CD 127. All right, and CD chapter 3. All right. All right, so I have exit e.c, so let's cat e.c. All right, so here I just made the simplest program I could. I include the standard Unix libraries, .h. Then I have a main function, and all it does is exit with 0. So it doesn't really accomplish anything, but exit is a syscall to terminate your currently running process. And we can watch what that happens. So I just compile it with the 32-bit switch to make 32-bit code, and the static switch to include a copy of the library in the compiled code just to make it easier to see. And so now if I've done that compile, so if I run this, it just returns. It just exits and returns normally. It doesn't accomplish anything, but we're going to look at how that works. So let's go into, let's get rid of this. Let's go into GDB in quiet mode of E. All right, and now let me shove this over to make more room. Okay, if I disassemble main, here's my main function. It's not very big, and so you can see it does some preliminary stuff, and then it calls exit, whatever exit is. So I'm in main, and it calls exit. So let's see what exit is. Exit. Exit calls run exit handlers, prepares some stuff and calls this. So let's see what's in there. Disassemble that. All right, and here, this is bigger. It does a lot of junk. And then get down far. And exit handlers is going to call underscore exit eventually. There. It eventually calls underscore exit. And now if I disassemble that, that has int80. And it also has another way of doing it, call %*%gs:*x10. These are both system calls. Here's one of them, and here's another. This one does the FC system call, which is, I think, 252, and this one does the one system call in EAX. So we'll talk about these. It does 2 syscalls, ultimately, after a bunch of preparation. All right, and so there are 4 ways to perform a syscall, by the way. int80, sysenter, call this *gs thing, and syscall on AMD64. They all do the same thing. For some reason, you don't always see the same thing in assembly code for syscalls, but all these do the same thing. All right, so we disassembled exit, and we can see it does 2 things. It goes syscall of 252, And syscall 252 is exit group to kill all threads. And syscall 1 is kill calling thread. So this is the correct way to terminate a program that might be a complicated program with many threads. First you kill the other threads, then you kill the main thread. So that's why exit is got 2 syscalls to do a proper exit from a program. All right, so now we can write shellcode that does this. And to write shellcode, you write it in raw assembly. Now you can start by writing it in C and compile it to get an idea what the assembly code could look, but you can see this assembly code was ridiculous. It went through like 4 functions, and one of these functions had 4 or 5 pages of code. So just to exit was like hundreds of assembly language instructions when you're going through the C library. And you don't need all that. You can make it much simpler. So it's better to write it yourself in assembler, but if you do that, it's going to have no error handling. If it crashes, it will just crash. This is something that bothered me when I started doing, using Metasploit. If you make a Metasploit shell and you execute it on a box by compromising it, if anything goes wrong, it will just crash with no explanation. For example, if it tries to make a network connection and that server does not respond, it will just crash. You don't get error messages or anything. So that's what the penalty of writing shellcode. Shellcode is supposed to be small and efficient, but you sacrifice all the luxuries. So we want to do the simplest sys exit call. We want to do the EAX equal 1 syscall. Now there is a syscall reference that lets you see these. Let me see if I can get this open in a browser. Link 3M, 127. Let's see how it looks if I try to open this in a browser. I got to get it fit on the screen. All right, let's see if I have 3M. There we are. Linux syscall reference. Oh, blast. This looks like somebody took it down. All right. Anyway, sometimes you can find them online. And all right. All right, now I see a question about grade 1, but I don't know what that is. I'll try and figure it out after the lecture. Anyway, so, all right. Anyway, it's here. And let me just see if I can zoom in on that then. Let's find a zoom here. View. Should be a zoom. If I go to format, opacity. All right, where's the bloody zoom? It's usually up here somewhere. There it is. Good. All right. Let's go up to 200%. There, now you can more or less see it. All right, so here's what a syscall reference looks like. Here's the EAX. So here's 1 is sysexit. And EBX is the error code coming back, and no other registers are used. So this is a simple example. There'll be other syscall references on the internet somewhere, including directly from Intel, I think. But anyway, there's other things like fork, read, write, open, close, and so on. All the basic functions are here in the kernel, and this, looking at the references, is how you learn how to execute them. But this one is very simple. All you need to put is 1 in EAX, and the return value will be in EBX, and you can just ignore the return value if you're a sloppy hacker and you just want to write shellcode. So that's EAX and EBX. So the assembly code we need is just this exit.asm. So if I look at that, get out of here, and cat exit, ASM I say. All right, what's going on here? Oh, it's exit2.asm. Let's see what this is. Nope, that's not it. All right, so I lost my source code for exit.asm. I'm going to put it back in. All right, and that's going to match this. Let me just shove it to the side. This is the assembly code. So global, you have a global symbol called main, which is how you're going to start the code. And you only have one section, which is the text section, because all I have is machine language instructions. I don't need a data section or anything. So main is here. This is where the program is going to start. And so I move EBX 0. That's a place to put the return value. I'm not sure that's entirely necessary, but it's recommended. EAX 0, EX1 to do syscall 1. And now I int 0x80. There. That should do it. That should perform an exit. Like I said, I'm not sure you need the EBX, but anyway, it works with the EBX. So I save this. Now I'm going to compile it. Now to compile it, I need an assembly compiler. And for that, you use NASM. And you can do it with sudo apt install. And there's NASM. So I'll compile it as before, NASM minus F elf 32 to make 32-bit assembly code from exit.asm. All right, and that creates this file exit.o. That's the object file. It's not an executable yet, but it's object file. You have to link it, and you can link it with the GCC compiler. Minus M32 to make 32-bit code, making an output of exit, and taking in exit shellcode. The output's going to be an exit shellcode. And the input is exit.o. So this takes the object file and performs the necessary linking to make a proper executable file. And now I have this thing called exit shellcode. And when you run it, it just exits normally. That's all it does. But we can look at what it's doing in more detail than that, and that's what we're going to do. Let me make this a little smaller. Let me go back to fit and put it here to get it kind of out of the way. All right. So now we can use objdump to look inside there. If you do a file on it, file tells you what kind of file it is. And this is 32-bit ELF code, executable. So it's a normal 32-bit executable program. If you do objdump, a very useful thing to do, minus D, this will show you the assembly code for the program. And so I give it exit shellcode. All right, and there it is. It's kind of big. This is the assembly code of all the pieces. But here's the main routine, which is the only thing I care about. And so this is the one I put 0 in EBX, I put 1 in EAX, and then I did int 80. So this is the raw hexadecimal bytes required to make that program. 5, 5, and 2, a total of 12 bytes to execute this in machine language. This is the machine code, the binary machine code. This is the semi-readable assembly code intended to make it easier for humans to read it. This is what the processor will process. So, I can test it with C code, which I wrote here, exit2.c. Let's see. Exit, test exit.c, perhaps that's it. I don't seem to have my conventions as clear as I should. Yeah, this is it. That's the code we just saw. If you go back here, this was BB and 0, BB8, 0, 1, and 0, and CD80, and that's what we have here. Those are the 12 bytes of hexadecimal code that we wish to execute. And this is a way you can test it. You can write a C program that creates a character array with all those bytes, and then with this crazy stuff, with all these pointer indicators, you can create a function that points to the start of that array and executes it as code. It's a little bit convoluted, but that's how you do it. And so if you compile this and run it, which I've done, it's just test exit. All right. And it just returns normally without crashing. So I mean, all this does is put this shellcode in memory, execute it, and all the code does is exit. So the only thing we're seeing is it runs without crashing. But the point is, this is the essential activity of injecting code in the box. So when you compile it, by the way, you have to have an executable stack, because this variable is going to be on the stack, and then you're going to execute it, and so on. Now we're going to use strace to see all the system calls. So if you use strace, it shows you all the system calls made by the program, and it turns out there are a lot of them. Let me make my window big. All right. Was it test exit? All right, let's see. It's there, test exit, so what's the deal here? All right, let me check. Maybe I need a parameter or something. Okay, strace, test exit. All right, what have I done wrong? I do ls. There's something called test exit. If I run it, exit. Okay, it works. Oh, I probably have to put in the /. Okay. There we go. So now this tells you everything about how this runs. It calls exec-ve to launch this process. It creates a process, and it tells you everything about the memory regions that are allocated and how they're whether they allow read or write, and so on. This is the kind of information you'd see in a debugger, the memory regions, the memory map, and everything else. But for right now, all we care about is right at the end, it runs exit 0. So that shellcode does the same thing the C program did. It executes an exit 0 after all the preliminary work of allocating memory regions and putting the right permissions on it and so on. And that's what all these things do, like memory map. These create memory regions and connect it to the right libraries and all that jazz. So it's quite a big chore for Linux to set it up and run it, but the end result is it runs exit 0, which is what we wanted to do. So now we can talk about why this is lousy shellcode. If you look at this shellcode we just made, it's got a whole bunch of null bytes, BB0000, B801000, and then CD80. And the problem is, usually, when you are performing an attack, you're entering data into a text field. Now, sometimes you can insert binary data, including zeros, and some of my projects are set up that way, so you can use this kind of shellcode and it's fine. But most of the time, you're injecting it in a field that is taking strings, like a username or a password or something like that. And if you put a null byte in, it will terminate the string. So you can only put one null byte in your injection, and it has to be the last byte. Everything after that will not enter the character array because it will be interpreted as having terminated the string. So for usable shellcode, for a general exploit, you have to get rid of those null bytes. And for that, you're going to have to stop using GCC because the compiler will compile code and almost always insert those null bytes. And we used assembler, but even assembler will typically put in null bytes unless you carefully choose the right instruction. So here, this instruction contains nulls. Move EBX0 has 4 null bytes because this is the 32-bit 0 that goes into there. So to avoid that, you use XOR EBX with EBX. That's a command that will, to every place XOR, if you combine 2 bits that are the same, you get 0. If they're different, you get 1. So if you do an XOR of EBX with itself, the answer is always 0. So this will put a 0 in EBX, but the command does not explicitly contain a reference to an absolute value 0. Now here's one. Putting 1 in EAX will have 3 bytes of 0 because the 1 is a 32-bit number with 3 bytes of 0 and then a 1 in the least significant byte. So you move AL1. This is only going to move 8 bits, and therefore there's no zeros in it. I've always wondered why the high 3 bytes are also 0, but in practice they are. So anyway, that's how we can improve our shellcode. So here's the comparison of the old and the new. The old shellcode had move EBX0. Now we're going to have XOR EBX. The old one had move EAX1, but now we're going to move AL1, and the int 80 remains the same. So this is my exit 2. So let's take a look at it here. I can make this window smaller again. All right, so we can cat exit2.asm. All right, so there's the new shellcode with XOR to put in the 0 and move AL to put in the 1. And when you compile this one and link it, it also works, of course. I make exit 2. All right, looks like I've got to make it again somehow. Exit 2 shellcode. Okay, exit 2 shellcode. All right, there we are. It runs and does the same thing. But what's more interesting, of course, is to look at the obj dump of it. So obj dump minus D, we'll look at that thing. I got to spell dump right, though. All right, and now I'm going to look at this thing, exit 2 shellcode. Don't think I need the / in this one. All right, there's all the assembly code in there. And if I just scroll back and find the main routine, here it is. So it's 31 dB for the XOR, it's B001 for the move 1, and CD80. Now it's only 6 bytes long, and none of them are 0. So this is much improved shellcode. It's smaller and it doesn't contain any null bytes. And that's the art of writing shellcode. Now, all these shellcodes we've written just do an exit, so they don't accomplish anything, but they show how to call a C library, and now that you know how to do that, you can do anything. So, spawning a shell, the next logical thing is to start a new process with a new command line available. And of course, what you'd really like to do is also connect it to a network socket, but for tonight, we're just going to make one that makes a new process on the same command line. So instead of using exit, we're going to offer the attacker a shell, and so You write high-level code, compile it, disassemble, analyze the assembly, clean it up, removing nulls, and now that's how you create shellcode. If you want to create it from scratch, we're not going to create any shellcode from scratch in this course. There's one project where you do a little bit. We're mostly just going to use Metasploit shellcode. The program creates the shellcode for us, but this is how you write shellcode if you want to. So 2 ways to create a new process. exec VE will take your running process, create a new one, and terminate the first one. That's one way to do it. Another way to do it is fork, to make a second copy of a process. So the first one keeps running. These are the 2 ways to create a new process in Linux. And man exec VE explains how it works. It is a little screwy, this command. It will execute a program. It causes the program that is currently being run to be replaced by the new program with a newly initialized stack and heap and all other data segments. So the original program is gone and the new program takes over. So this is one type of shell to create. All right, so if you want to use exec VE, that's this one. And I think I've got it here. Cat exec ve.c. All right, so here we are. The exec VE format is screwy. For some reason, you have to give it the same data several ways. You have to give it a pointer to an array shell, which will include the name of the shell you want to launch, and then other parameters, which would be a null. We're not doing the fancy stuff. And the first one has to be this same thing. You have to put the shell here, and you have to have a pointer to the object containing the shell here. It's screwy. You put the same data in twice, essentially. But anyway, that's how you do it. That's what exec VE does. And so if you run that, it opened a shell, and notice the prompt changed. Now, if you want to know what shell you're in, let me exit and get back to where you are. If you want to know what shell you're in Linux, you do echo $0. $0 is an environment variable that tells you what shell you're in. So right now, I'm in bash. If I run this exec VE, and then echo 0, now I'm in sh, because that's what I told it. I wanted to run sh. And sh is, I think, the default shell for the box. It's different than bash. So you can see I am in a different location. And by the way, if I do who am I, I'm Debian. Okay, I guess that's going to be the same. If I exit and do who am I, I'm okay. I didn't change who I was, but I did change my shell environment. So that's the, anyway, I've now spawned a shell that's different than the original one I started from. And that's the, that's an example that does a little bit more than just exit. All right. And so you can look at it in the assembler, in the debugger, gdb -q exec VE. All right, and now I can disassemble main. And what I want to find here is the part where it calls exec VE. So here's where it calls exec VE. And so before that, it's going to push the arguments on the stack. So here it pushes a 0. Here it pushes this ECX, which is pointing to a location on the stack, EBP -10. And here it pushes EDX, which is going to be a null. There'll be a null in EDX. And so if we look above this, let me make my window a little bigger. Oh, here we are. So up here someplace, up here it is. This putting this pointer in EDX. Anyway, so that's the point. Here it is pushing these things on the stack, 0, ECX, and EDX, and then it calls exec VE. So this is the setup and call. And I'm not, yeah.
How do people attach to the process?
Attached to the process? Well, when you make the process, you specify where the input and output is. You specify a device number. Normally you take input from device number 0 and output to device number 1, I think. Yeah, standard in is 0, standard out is 1, and standard error is 2. So if you connect to those device numbers, you have this kind of shell where you're taking input from the keyboard and putting the output at the console. But what you do is you open a network connection and it gets a device number. And then you make the standard input and standard output go to that device number. So
like some of the hacking tools, they attach to like certain hosts.
Yeah, your debugger can attach to a process. So what it has to do is stop the process and inject something into it and then run it again. And I don't know exactly how it works at the binary level. I know it, yeah, it's a good question, and I've never looked into it. It'd be nice to know exactly how a debugger does that attaching. Anyway, that's what the exec VE call looks like. And so, all right, and by the way, if you disassemble the C-compiled exec VE, it does quite a bit more, putting 4 parameters into all these things. Anyway, all right. So anyway, I mentioned before there are various different versions of syscall. The int 80 is the old-fashioned one. There are some modern ones. And anyway, here's one from your book that's a more complete shellcode with more of the details. So it can get pretty complicated, but yeah, hopefully you have a general idea how it works is all I'm planning to do here. And you can test the final shellcode and see that it works, but I'm not planning to go through the details of much in the book. So that's as much of that as I wanted to show you. Let's try a Kahoot, and then I'll just demonstrate other projects, starting with the SQL injection and moving on to other projects as far as we can get. So I want to do Kahoots. Log in. All right. Come on. All right. 127, shellcode. There we are. All right. Let's see how many people are in the chat room. 16, all right, and 1 in the room, so 8 or 9 might be all you're gonna get tonight. I'll give it a few more seconds and see. Seems to be only about half the people are doing Kahoots this semester. They're optional. It's your chance for glory and fame, however. All right. All right, so what item will convert executable code into assembly language? All right, yep, obj dump does it. Takes an executable program and extracts the assembly language from it. Can do other things too, but that's the only thing we've done with it so far. GCC does the opposite. That takes source code and converts and turns it into executable code, but doesn't ever pass through assembly language. And NASM takes assembly language and compiles it into executable code, so it again does the opposite. Obj dump is what is doing the reverse engineering thing that we're doing of taking a compiled program and trying to analyze it without the source code. All right. Which one will list all system calls? All right, strace, that's what it does. It's kind of a mess, but it's really a text representation of the same kind of information you get from a debugger, like Ali debug we'll be using later. All right, which item goes from user mode to kernel mode? that's syscalls. Good. All right, which one will convert assembly code into object code? That's what NASM does. It compiles the assembly code into object code, which you then link and then turn into an executable program. All right, what instruction should be used to replace move EAX 0? That's it. The XOR with itself will put a 0 in there without directly, explicitly referring to the number 0. And what instruction should we replace move AX1? That one gets rid of the nulls and it's nice and compact. By the way, you could do an XOR and then do an increment, and that would also do it, but it would be more bytes. This is only 2 bytes, so it's small and it avoids null bytes. All right, I got chickens. I bet that's faces the student that doesn't care about points. And that's Sid, okay. And that's Bee Honey. Good. All right. So I've got the winners, and I'm going to stop this recording.